Good morning. Welcome to another warm Friday. Seems more like August than September right now. We are going to continue our conversation of transmission topics. And what we're going to do today is to continue to review how one analyzes planetary gear sets using something that is called the lever analogy, which later you will understand today why it's a good idea to introduce this. And once we have done this preliminary initial review of the lever analogy and how you analyze the relationship between the different sun, carrier, and ring gears in a planetary gear set, then we'll be prepared to begin an analysis of electrically variable transmissions. So I'll start with the lever analogy, and I will bring you back to high school physics for a moment. Everyone understands the principles of a lever. I know in Italian, datemi una leva e solleverò il mondo. This is Archimedes, it was? Is that who said that? I think so. Anyways, basically, in English it goes, give me a lever and I will lift the world, right? So the idea now is that you have three elements in a lever. You have a fulcrum, then you have an end where you apply an effort, and of course a load, which is what you would like to move. So we're going to define two distances, two dimensions, A and B. And here is the effort represented in terms of a force, and here is the load also represented in terms of a force. So clearly, what happens is that these two forces act in the same direction, and what happens at the fulcrum is that you have a reaction force. So far, so good. So what makes the lever so useful is that the ratio between the effort and the load is equal to the ratio between B and A, these two dimensions. So if you make B small and A large, as we all know from practical experience, you can, with a relatively small effort, do a lot of work, lift a really large load, for example. Okay. So what we're going to do now is we're going to interpret gears engaged with one another in the same way as we would interpret a lever. Okay. We're going to make some simple assumptions. This is no friction, and which, by the way, you know that a single gear pair can have an efficiency of 98, 99%, so the no friction part is not a big deal. That's a reasonable assumption. And no inertia. Of course, this is not true technically, and if you were to develop a true model of a gear set, you would have to take into account the inertias of the gears. But for our purposes, we're not interested in the relatively high frequency dynamics. We think of this as a quasi-static system. Parenthesis, there is a paper that was written by us in collaboration many years ago. This may have been in the days of the Challenge X competition. We had a visiting scholar from Politecnico di Torino in Italy, who's now an associate professor there, who did some fantastic work in helping us model in detail the transmission dynamics for this particular vehicle. And so there is a paper in the context of drive quality, drivability. I'll have to come up, Claudia and Daniele, if you remind me, I'll find that paper and we can put it in the reading materials in case someone is interested in seeing what it would look like if you actually truly had planetary gear set dynamics incorporated in the model. So let's imagine now that you're going to have, in this case, a driving gear, right? You have some input torque here that comes, for example, from the engine. And so this gear is rotating at its angular velocity omega sub 1. Then you're going to have a load torque, which is going to be the other end. In this case, it would be the output shaft of the transmission. And you can see, why do I say load torque? Because T2 is in the opposite direction as omega 2, right? So it's opposing the torque imposed by whatever the input is. Now, there are basic kinematic relationships. So I'm only talking about kinematic models, no dynamics here. And the basic kinematic relationships will tell you that the ratio between omega 1 and omega 2 is the ratio between the teeth N2 over N1. And there is a minus sign here because the velocity, the rotation of the output gear is opposite to the direction of rotation of the input gear. Similarly, the torque ratio, T1 over T2, is going to be N1 over N2. So you can clearly see that this should be immediately obvious to you, that if N2 is greater than N1, then you're going to have a torque ratio that is less than 1 between T1 and T2, but a speed ratio that is greater than 1, or vice versa. Depending on the number of teeth, you will have a speed increase and torque decrease, or vice versa. If N2 is greater than N1, then you're reducing the rotational velocity and increasing the torque. So if this is a gear that is coupling the engine to some output shaft of the transmission, this would typically be the case, because what you're interested in is reducing the velocity of the internal combustion engine to match it to the velocity of the wheels, and of course increasing the torque so you can produce the thrust that the vehicle needs to move. So now we're going to represent this in the context of a planetary gear set. So I just showed you a gear pair in the previous plot. Now let's go to a planetary gear set. Let's imagine now that omega r is equal to 0. In other words, I have somehow, through a clutch, right, locked the ring gear, which means that the only thing that is happening is that you're going to have planet gears rotating in some direction. This shows like this, and the sun gear is rotating in this direction. So this is the same as the gear pair I showed you in the previous picture, because I have locked the ring. Now, let's imagine now that to talk about, so the thing about planetary gear sets that could be confusing at first is that you have two things that happen. You have rotation, but you also have revolution of the entire system. Okay, so what we're going to do, let's imagine now to start that first we lock the entire assembly and rotate it one turn counterclockwise, okay? And this means rotating everything. We know that the ring is fixed, but so we can further decide that counterclockwise we're going to call positive direction. This is arbitrary, doesn't matter. And clockwise we're going to call it the negative direction. So then the way this works is that the carrier is going to rotate at a speed that is related to the sun angular velocity of rotation by the ratio of the sun gear number of teeth divided by the sum of the sun gear plus ring gear number of teeth. And the reason you have to have the ring gear here, because everything that happens between these two gears is relative to the fact that they're encased inside the ring gear. So now I am going to construct something that begins to look like the lever analogy. And what happens here is I have fixed the ring to be at 0 speed. Okay. Then I am going to have a carrier that is rotating at a speed omega sub c. And if the carrier is rotating at a speed omega sub c, oh, and by the way, this n sub s and n sub r, the number of teeth, are similar to the AB, they're equivalent to the AB distances in the basic lever that we saw in the first slide of this lecture. And so finally, the sun is going to rotate at a speed omega sub s. So we're using, in this sense, we have kind of an odd lever, not that odd, it's just that one of the values is 0. So now, let's imagine that we hold the carrier fixed and now rotate the ring clockwise one turn. So then what happens is that if I rotate the ring clockwise one turn, the planet gears, the pinions that are connected to the carrier, will rotate NR over NP turns also clockwise. So now what's going to happen is, since the planet drives the sun, and the planet turns nr over np turns clockwise, the sun will also turn because it's being pushed by the carrier, by the pinions, and it's going to turn, as it turns out, you can look at the arithmetic here, but it's going to turn minus nr over ns. This one is going to go counterclockwise. So in this lever analogy, what's going to happen now is that my fixed point, because I locked it, is the carrier. Now the ring is going to rotate at velocity omega sub r in one direction, and the sun is going to go in the opposite direction, and the ratio of this speed to this speed is given by that expression. And there is a minus sign now because they're rotating in opposite directions. So now I can take a look at the complete picture here, in which in one case I lock the ring, in one case I lock the carrier, and here is another case in which I am not necessarily locking any of them. They can rotate with respect to one another, so that you're going to have some velocity here and some other carrier velocity here and a sun velocity there. And this is the most general expression that always has to be satisfied because of the kinematic relationships. So the purpose of this explanation is to illustrate to you, it may take a little while for you to digest this, but the point is that the reason we're doing this is because oftentimes when people explain the behavior of transmissions, they show it quickly using this lever analogy to show you the relationship between the speeds and also the directions, okay? So having some familiarity, if nothing else, with the graphical notation, understanding when you see a lever like this, you're really looking at the kinematic relationship among the three gears. So this analogy, when you combine all of these things, is going to determine the rotational speeds of the gear set. Okay. So depending on what is locked, on what is not locked, and the number of teeth that you have, that gives you a fixed set of kinematic relationships among the gears. Now, if you want to calculate the torque, well, you're going to have to, the way to do it is to assume that power is conserved. That's why we said no friction. Okay. So with efficiency 1, what happens is that the power at the ring gear must be equal to the power at the sun minus the power at the carrier. And so if you then combine this relationship, this conservation of power expression with the speed expression we have, then you can also determine all of the torques. So you're using kinematics to determine the relationships among the different gears, and conservation of power for the power equation. What's left for you is the torques, and you can come up with the relationships for the torques. I'm not going to say anything about this. I think we've just, what I have explained is sufficient for the purpose of what we're doing. Now, this is then, by doing a moment balance or a torque balance, how you would calculate the relationship between the torques. So you have the ring gear torque related to the carrier torque, and the sun gear torque related to the carrier gear torque by those relationships. Okay. This was just an overview to introduce you to some diagrams that we're going to show. What we're going to now talk about is the idea of an electrically variable transmission. And this is not a new idea. First of all, I told you that planetary gear sets are about 2,500 years old. The Greeks had them figured out already. Okay. But the idea now is that if you now have 3 gears, okay, and then you have 1 input, plus 3 gears, plus 1 output, and you can decide where each input and output is going to be. For example, the input could be on the ring gear and the output could be on the sun, or vice versa. The input could be on the ring gear and the output could be on the carrier, and vice versa. So when you look at all the possible combinations that you have, I'm going to show you in a moment what is possible here. In fact, if you just take 3 gears and now allow for the possibility that you're going to have 2 electric machines, right? Because that's what these EVTs consist of, then now you're going to have the following degrees of freedom. You're going to have 1 where you put the input and 2 where you put the output. But in addition to that, you're going to have to decide where to put, let's call the machines MG, motor generators, because each machine can always be a motor or a generator. So I'm going to say MG1 and MG2. And you have the option to put each of these machines on any one of the 3 gears. You won't put both machines on the same gear because that would be stupid, but aside from that, as long as the 2 machines are on 2 different gears, they could be MG1 on ring, MG2 on carrier, et cetera, et cetera. We're going to call one of these machines, we're going to call the regulator motor, because you will see that that machine is going to be used to regulate the speed of the engine, or to regulate in general the speed ratio of the transmission. And the other one we're going to call other motor. It turns out that if you just take a planetary gear set with these 2 inputs and then 2 electric machines, there are 12 possible configurations where you would have the possibility of selecting. Remember, you have 3 gears, so on the sun, you could have, for example, the input and other motor, or you could have the output and other motor, for example. These are configurations that are possible. Then you would have, on the carrier, you could have, say, regulator motor and no input or output. On the ring, you could have input regulator motor or output another motor. So there is a number of combinations that make sense that you can do. It turns out that there are 12 EVT configurations. And this work was done by a student, Alan Holmes, who was team leader for the Future Car competition in the late 90s, 98, 99, and who went on to work at Allison Transmission. At that time, Allison Transmission was a division of General Motors. It's based still to date in Indianapolis. Today, Allison is an independent company. It's been separated from GM. But there was a time in the 1990s, early 2000s maybe, when a group of people, in the 2000s, when a group of people from Allison Transmission who had been responsible for the development of an electrically variable transmission architecture that today still is made for buses. So this is for commercial vehicles. It's a pretty large object. So GM, through Allison Transmission, was making EVTs, I think before Toyota came out with the Prius. This is something that has been in place for quite some time. A group of people, including Alan, was transferred from Allison Transmission to GM Powertrain, and they were responsible for the development of what was called the 2-mode hybrid, which was a product that GM launched, and at some point they had an agreement, a technology sharing agreement, where Daimler, Chrysler, and BMW actually shared in the technology. GM licensed the 2-mode hybrid to them as well. It turns out that the 2-mode hybrid was never quite successful. It's an engineering, great piece of engineering, but it's a bit on the expensive side, maybe a little overly complicated. But anyways, what I wanted to say is that Alan, who came out of the great-grandfather or great-great-grandfather of the EcoCar program, a future car, ended up having his name on something like 100 patents related to EVTs or some crazy number like that. I see him every now and then. So these are all the possibilities, and it turns out that the one that is circled here is the Toyota Prius configuration. And it's a carrier-to-ring input split in which you have the regulator motor on the Sun, the input on the carrier, and the output and the other motor on the ring gear. I will describe it in pretty good detail. So here is another, and by the way, Alan did a master's thesis here, and his master's thesis is just a high-level analysis of all the possible configurations that you might be able to have with a simple planetary gear set. Let me also say, it'll become clearer later, but this is a very, very simple analysis because this is an EVT that does not have any clutches, which is one of the beauties of the Toyota system. It's as simple as you can make it. So here's what happens. I'm going to continue using a convention whereby, for no particular reason, the Sun is green, which is not true. We know that. The carrier is blue, and the ring gear is red. Okay? So what happens now is in this configuration, the engine is connected to the carrier. So what happens now is this is a mechanical connection of the engine staff to the carrier. And this in blue with two sides is a schematic representation that shows you that you have a gear set. Okay? Next, what's going to happen then in this configuration, the motor generator set that we're going to call the regulator is going to be connected to the Sun. So this is the Sun gear here, and obviously that shaft that comes from the engine goes through that Sun gear. And what are these odd things here? We haven't talked about electric machines yet. That's a cross-section, a cutout of an electric machine, such that the black rectangles are the rotor, and the dashed rectangles are the stator. So if you cut an electric machine in the appropriate direction, you would have a gap. This is the gap right here in between. Outside the gap, you have a stator, which is where the windings are, and inside the gap, you have the rotor, where in the type of electric machine used by Toyota, that's a permanent magnet rotor. So it's got some iron and some permanent magnets in it. So far, so good, because these are diagrams that conceptually represent something that is much more complicated to actually see. I'll have pictures of the real thing, but if you just look at a cutout of a real GM EVT, Toyota EVT, it's not so obvious what's going on. Finally, we have, oh, I used the wrong color for the Sun. After making all that fuss about colors, I went red when I was supposed to go green. Sorry. I'll get it. That's supposed to be the eraser. There you go. So, sorry, the Sun is green. And finally, what happens now is the output goes from the ring. Mechanically, it's connected to the final drive. That's how the ring gear comes out. But there also is another electric machine that is wrapped around on the same output shaft. So the shaft of this electric machine connects on one side to the ring gear, and on the other side goes out to the driveline differential half shafts, et cetera, et cetera. Okay. So I took a minute to explain this, and because then the mechanical power flow goes through the differential to the wheels. Okay? I am going to briefly mention that that configuration is one configuration. You could also do configuration shifting. In other words, by having clutches, you could lock different elements in different ways, and so you could actually change the configuration. So you might have a different type of behavior beyond what you can achieve with this Toyota hybrid system if you added clutches. Toyota made the decision to keep the system as simple as possible, and at some point, maybe in this lecture, maybe later, I will explain to you what the trade-off is for this simplicity. As always in engineering, nothing is, you don't get anything for free. So if you have a simpler design, you're giving up something. So the absence of clutches does have a drawback that needs to be considered. Second, so that's configuration shifting, where if you have one or two clutches, every time you engage or disengage that clutch, you essentially have a new configuration. So out of the table of different configurations that I had in the beginning, if I have a clutch, I could, by actuating the clutch, generate another set of configuration. The second thing that you can do is called compounding. And this has been done in production. In fact, the GM two-mode hybrid, the Chevrolet Volt, and later generations of the Toyota hybrid system use compounding. What does compounding mean? Compounding means that you still have two electric machines like we did before. One is a motor, one is a regulator most of the time. But now you're going to have planetary gear set PGS 1 and a second planetary gear set. So now you are actually taking advantage of the fact that you have two planetary gear set, which gives you more opportunities for achieving different kinds of gear ratios because you have two planetary gear sets. Each complex EVT, whether you use configuration shifting or compounding, is going to have advantages and disadvantages. And here, Alan, in his thesis, gave an idea of what are the advantages. So, for example, just to take a peek at this, the basic EVT, that's what I'm calling right now the Toyota hybrid system, has pretty good efficiency. Motor size not so great because you don't have enough gear reduction to allow you to reduce the motors. The moment you go to compounding and you have two gear sets, you can get more leverage from your gears because you have more gears, therefore you could make the motor smaller. So you can see that when you have configuration shifting or final drive shifting, you have a better. Smoothness is very good. Gears, few, that's an advantage. Clutches, none. So these are the definitions that are important. This is a very qualitative table, but to show you that there are trade-offs. So now, let's go back. Darn, I made a mistake. In this diagram here, I have green, red, and blue, but I'm going to go back and rewrite. It turns out that the carrier was red. So don't change this in your notes, but and the ring is blue. Darn, I wish I had looked ahead a little bit to not make that mistake. Sorry about that. But we're going to take a look now at the simple EVT configuration one more time. So you can see, as I have described before, that the shaft coming from the engine goes through the carrier, through the, that there is a regulator motor that is going to go to the sun. That's right here. Then there is going to be the engine that is connected to the carrier. So that is coming from the engine, right here. And finally, the ring gear is the output. So these are the mechanical connections. What happens now is that you're going to have an electric machine here, Mg1, and you're going to have an electric machine here, Mg2. That, again, is the same picture of what we've already seen. If I give you, by the way, gosh, this looks like a homework assignment kind of thing, right? If I now give you this configuration, what have I done here? I have drawn a line across the middle here, and I have preserved only the top part of that drawing. So now we have simplified a sketch, which is actually a three-dimensional structure in which you have through shafts and all kinds of other complicated things. And I have turned this into a simple two-dimensional structure in which I'm going to have an electric machine connected to this shaft. I'm going to have the output shaft coming from the carrier that is also going to have an electric machine, from the ring that is also going to have an electric machine, and the carrier is actually connected to the internal combustion engine. So what you can do now, you see that you now have a set of predefined relationships, and we already know all the expression to relate the ring torque to the carrier torque, the sun torque to the carrier torque, the ring speed as a function of carrier speed and sun speed. And again, in steady state, power is conserved. So fundamentally, these are the two relationships that we're going to use for that. And if you look at a lever analogy, fundamentally, when this is a free-floating transmission, these are the relationships that you have. You're going to have NS teeth between ring and carrier, NR teeth between carrier and sun, and then you're going to have these speeds, omega R, omega C, omega S. What's going to happen now is so pay attention because this is the key idea. The way the system works is that in absolute terms, if I locked one of the gears, then the relationship between the other two is fixed. But what if I could vary the speed of one of these gears arbitrarily, any way I want? How could I do that? Very simple. I can put an electric machine, for example, on the sun gear, and impose a speed to that machine through my controls. And basically what I'm going to be able to do by changing, that's the regulator. That's why it's called regulator machine, because it regulates the speed. By changing the speed of that machine, I can essentially move that lever diagram to different places to achieve different things. So what an electrically variable transmission does is it adds to the normal properties of a planetary gear set the ability to arbitrarily change one speed, so that, and you can change it so that you can move these relationships back and forth. Let's take a look at an example EVT, and one more time, I quit on this green, red, and blue. Every diagram I bring up has a different green, red, and blue thing. Maybe one of these days I'll uniform all of that. Make a note, Daniela, please. Okay. So anyways, these are just general configurations in which, so let's see, what transmission is this? Well, this is clearly, as I've been saying all along, is the Toyota Prius drivetrain, because you have the engine on the carrier. I have the MG1, the generator or regulator, is on the sun, and the output is to the final drive, and I have the machine MG2. By now, hopefully, you're familiar with that configuration. But here is one of the other things I could do. I could have two brakes or clutches, okay? Let me explain it qualitatively. This is just one example, but what would you have these clutches? You could do this. You could have one that allows you to get more torque leverage for launch. So it's one that makes the launch of the vehicle better. You could then have another brake that would change the behavior of these EVT so that when you're cruising, cruise control 70 miles per hour on the freeway, okay? Do you need the hybrid system? Wouldn't the most logical configuration be to simply have the internal combustion engine, steady state, drive the gears directly to the wheels, to the differential and then the wheels? Why not? Because in the end, who needs a hybrid electric energy conversion when all you're doing is going at a steady speed? The most efficient thing you can do is to actually simply use the internal combustion engine. You don't need to do any additional energy conversions, because remember that if you do any further energy conversions, you have losses. Losses in the electric machines, losses in the power converter, losses in the battery. So the truth is that in a hybrid electric vehicle, if you are cruising at steady speed on the freeway, engine connected directly by some kind of a gear reduction to the wheels is the best, most efficient way to go. So now I go to the comment I made earlier. The Toyota Prius cannot do that. It does not have any clutches, even brakes, and so it is impossible for the Toyota Prius to simply lock a final gear drive and say, you're going 70, here you go, okay? No, the Toyota Prius is continuously recycling electrical power because it needs to use the regulator motor all the time to give you the CVT, continuously variable ratio, to keep it in the right place. So even when you're cruising at 70 miles per hour on a flat road, in the Toyota configuration, there is a lot of electrical power that is moving around. And it's all being recycled and reused, but there are losses. So in principle, why was the introduction of the Toyota Prius so interesting? Because for the first time you had a vehicle where your city fuel economy was equal to the highway fuel economy. You can get 45, 50 miles per gallon in the city and on the highway. But in fact, a criticism you could bring is that you could do better than that on the highway if you had a clutch. So you could say that if the Toyota Prius of that generation gave you 50 miles per gallon in the city and 50 on the highway, with a mechanical change in the configuration, which, however, would add complexity and cost, I don't rule this out, maybe you could get 50, 55, or 50, 60, something like that. Yes, there is a question.
Professor, in the previous diagram, so if the car is in cruising mode, then there is only one gear reduction and the power goes straight to the wheels. But we can cruise at 50 miles per hour, or we can cruise at 80. So does the system actually require us to have an additional transmission?
Does assume what? That you have what?
In this system, do we need an additional transmission after the planetary gear set? Because cruising can be done at multiple speeds.
Well, what happens, it's a good question. The question is, do you need multiple gears? Now, when you're cruising, what happens is that you have one, let me call it overdrive ratio, okay, which you can achieve by some ratio of gears in the single planetary gear set you have, plus the final drive. Of course, you're going to do at variable speeds, which means that your engine will change its speed. That's it. So you're just moving the engine, which is what a car does anyways today, a normal vehicle does. So you don't necessarily need another gear set. Of course, if you have another gear set, you have more opportunities, and that's what GM did with the two-mode hybrid. Okay, but it is entirely possible to do everything I said with a single planetary gear set. And I am just not going to go into the detail of this. What I want to point, especially because these diagrams are very generic. The point is that if you now start exercising your imagination, you could come up with a number of designs, and people have done this. I remember working with a company, I won't mention the name, years ago, who thought that somehow they had come up with a much better way of doing the EVT. Well, what they didn't realize is that others, like GM or Toyota and others, had already thought about it, and they had ruled it out for other reasons. But anyways, Yeah, so you can see here that there are many different kinds of configurations that you could do. So what I'm going to do here is talk a little bit about the GM two-mode hybrid. GM really developed it and then licensed its use to Daimler Chrysler. There was a time, I don't know if you realize that in 1998, Daimler essentially acquired Chrysler, and there was a company called Daimler Chrysler for a number of years. Then there was a painful divorce. Now it's Fiat Chrysler. The Fiat Chrysler thing has gone a lot better than the Daimler Chrysler thing, and I could talk to you for days about the history of these things because I was sort of in the middle of all these things. Having at that time in 1998, 99, I was working with both Daimler and Chrysler just before the merger, so it was an interesting relationship. What happens is that GM created this two-mode hybrid several years after Toyota had already commercialized the Prius, and it basically has two planetary gear sets. So what happened, this is what you were suggesting, Yuvraj, so your comment was quite appropriate. By having two gear sets, you can actually have some of the capabilities of a conventional automatic transmission. And so in the two-mode hybrid, you could actually have fixed gear sets, much like an automatic transmission. And for cruising on the highway, that is truly a superior configuration. So in the GM two-mode hybrid, you have a total of 6 operating functions. You can have an input split, EVT, which you can call it continuously variable mode 1, which operates from launch through maybe the second fixed gear ratio. So you're doing all the things that the single planetary gear set Toyota system is doing, but in addition to that, you also have the ability to have fixed gear ratios like in an automatic transmission. Then you can have a compound split EVT mode, which is continuously variable mode 2, which operates after the second fixed gear ratio. So what happens now is that at launch, you have a configuration. After launch, by using clutches, you do a second configuration. And what happens is now you're really truly maximizing the efficiency and the performance by having this configuration shifting between the first and the second. Then you have a fixed first gear ratio to both electric motor that is available to boost the internal combustion engine or capture and store energy from regenerative braking, deceleration, et cetera, et cetera. So there is the system is configured so that if you need to add torque to the engine shaft, you can do it quickly, and if you need to do regen, you can also do that efficiency. Then there is a second fixed gear ratio with only one electric motor available for boost braking. So there are two configurations. In one of them, you can do regen and torque assist with two electric machines at the same time, MG1 and MG2. In the second configuration, you can do regen and boost only with one electric machine, which would be the output one. That one is always available. And so on. There are a couple of other configurations. So from an engineering perspective, this system is a beauty. From a complexity and cost perspective, not so good. So in 2008, this system was introduced. It was basically used for the larger SUVs, and it worked. But it was really kind of a gold-plated solution, very expensive. It could only really be afforded in the higher end, most expensive large SUVs. Here is the configuration that you see here. And just a brief outline of how this system works. Here is the engine input. There is a damper. These are things that you will always have somewhere in the powertrain. This shows it more explicitly. Then a hydraulic pump is powered at that point at the shaft. And then you can see that you're going to have one planetary gear set here, another planetary gear set here, and you're going to have MGA and MGB, the two motor generators, that's where they're connected. These beasts here are clutches, okay? And then you're going to have clutches and additional gear reductions here at the output. So this system is complicated at this stage in our class. It's not worth analyzing it in detail. We will analyze in detail the operation of the Toyota Prius system. But one of the things that is nice about this diagram is to illustrate to you something else that is very important in hybrid electric vehicles. You now have a system that has a lot of degrees of freedom, many. Why? In a conventional powertrain, the only degree of freedom you have from a control perspective is shifting the transmission. We've already seen that. We've understood that. Now, you have the ability to, in the simplest Toyota system, you have the ability to decide how much to use. You have two electric machines, okay? So those are two additional degrees of freedom because each of them can be controlled independently. So now you have, but you don't have the transmission shifting anymore because that happens by itself. So now in the Toyota, that's the beauty of the simplicity of the Toyota hybrid system. But you do have 2 degrees of freedom now, not 1. You've given up on the shifting because you don't have a stepped transmission, but you have to control 2 electric machines. No clutches, okay, that's as simple as it can get. In the GM 2-mode system, wow, I now have 2 electric machines, those are given. Then I'm going to have, let's go, can we go count the clutches? It looks like I have 1, 2, 3, 4. No, these are the same. 1, 2, 3, 4. There are 4 clutches, so I have to decide what to do with these clutches. So now I have 6 inputs. It is true that the clutches are one time, you know, you're not continuously operating clutches. You decide basically if they're going to be on or off. But when you actuate the clutches, you're essentially shifting mode of operation. So you have continuous controls over the electric machines, 2 degrees of freedom of continuous controls, and 4 degrees of freedom of discrete control, on-off control over 4 clutches. And depending on the clutch configurations, you can have different modes. So watch this. Oh, wait. But wait, there's more. Because in addition to that, GM employed in this system, they call it active fuel management. You could call cylinder deactivation, okay? Which means that this went in big vehicles that had V8s, but you don't need to have a V8 power all the time. So you have cylinder deactivation that allows you to use this as a V4 engine. So that's an additional degree of freedom. As a result of all these degrees of freedom, you have different modes. Yes, there are 2 primary modes, okay, mode 1 and mode 2, but then you have different gears that you can select on and different modes for cylinder deactivation. So what happens is that I'll walk through this diagram with you. Mode 1, electric drive, you're going to for low vehicle speed, initially you launch the vehicle electrically. That's something that always makes sense for any hybrid. Then you're going to have acceleration. Well, acceleration is going to like power. And also, it's good to be in a low gear, so you have a lot of torque leverage. Therefore, you have V8 power and you're in first gear. Now, you've launched the vehicle, first electrically, then you're using the V8 power. Now you've reached a certain velocity. At this point, you can relax a little bit. You've built momentum in the vehicle. Now you can do, if you're still accelerating, you'll do it with the V4. And not only that, but at this point, you're going to shift from mode 1 to gear from gear 1 to gear 2 to mode 2, because you're going to be shifting to the higher gears from second to third. Suppose now that I'm going at 45 miles per hour and the speed limit changes and I go into a 65 mile per hour range, so I'm going to accelerate, or I'm passing a truck or something. You can get your V8 acceleration again, but this time you're in third gear because you're already at pretty high speed. Later you're going to cruise while you're cruising V4, and if you have a slight acceleration while you're cruising in V4, you need again, you're making a passing maneuver on the freeway, you can get a little electrical boost. And then you can continue on this whole discussion and see what happens when you are in the regeneration mode. So it's beautiful. It is a moment of happiness for engineers to realize that they have developed a system that is so sophisticated, but it is really complex too. The end result is that this system did not really succeed in the marketplace. There was the development of something that was informally called the baby two-mode hybrid, but at the time that was intended to be a little simpler, smaller, lighter, and available for smaller vehicles. At the time when the baby two-mode hybrid was about to be launched is when the big recession hit in 2009, 10, 8, 9, 10, thereabouts. And so that program was canceled. But there is a nice ending to these stories because the folks at GM are very capable and knowledgeable and good. When later, post-recession, the Chevy Volt was announced, it turns out that the powertrain of the Chevrolet Volt plug-in hybrid vehicle is actually quite similar to, it derived from, it's an evolution of the two-mode hybrid. And at some point, I am going to talk to you more about this. Let's take a step back and talk about homework assignment 3. I think that the homework is due next week. Yeah. So what we've done in this homework assignment is to give you an M file which contains the engine maps for an engine. Thank you, EcoCar team, for supplying the engine data. So it's a 4-cylinder, 2-liter displacement engine. So what we're doing is we're giving you a program, an M file, and you are supposed to plot this fuel consumption map as a function of engine speed in RPM and torque in the form of a contour plot. This is just an exercise in writing plotting files in MATLAB, and there's nothing magical about it. But if there is one thing you should become very familiar with in your use of MATLAB is how to use it to generate pleasant-looking outputs so that you can show the results of the calculations you've done. Next, and this is more important, is you want to convert this as a function of mean piston speed and mean effective pressure. So now we're taking this dimensional map that is specific to one engine, and we're going to non-dimensionalize the map by computing, normalizing to mean piston speed and mean effective pressure. What happens now when you do this is that what you're going to have is an efficiency and fuel consumption map that is, you can think of it as the abstraction of any 2-liter gasoline engine of that type of configuration. In fact, it's the abstraction of any engine of that particular configuration. Is this direct injection? So is it boosted? No. So naturally aspirated, direct injection, 2-liter, okay? Once you've normalized it, you can then redimensionalize it to make it a 1.5-liter. Naturally aspirated direct injected engine. If you had a boosted engine, well, that map would be a different one because the characteristics would be different. So think of this as an abstraction of all naturally aspirated direct injected engines that probably would do a good job of representing anything between 1 and 3 liters in displacement. You can just dimensionalize it anywhere you want between those. So now, from this map, you can calculate and plot the engine efficiency as a function of speed and torque, and you can calculate and plot the Wilens line model for this engine, and we're telling you just do it at these speeds specifically. So discrete, it's a bunch of lines at each speed, like the plots that I have shown you in class. Next, we'd like you to do a quadratic curve fit. For what? For the slope and intercept of the Wilens line. As we have said in the past, the Wilens line is an affine relationship. By affine, we mean that it's a straight line that does not go through zero. Okay? And so what you can do then is, again, compare the Wilens line model and do a curve fit. The purpose of this is to have an analytical model of the engine. Then, again, obtain an appropriate curve fit for the maximum mean effective pressure. This means that what you're going to want to do is to get them, to get a curve fit also for the maximum torque, what we call the maximum torque. So basically, there are 3 things you have to do to make this map an analytical model that uses algebraic equations. You have to curve fit E, the slope of the curve. You have to curve fit PML, the mean effective pressure loss, the losses, and you have to curve fit the maximum torque curve. Okay. So now you can compare with the actual map, so you're going to show how one fits the other, and if there are any observations that come to mind that you want to make some comments. And now let's imagine that I want to say, gee, with this technology, direct injection and naturally aspirated, what would happen if I wanted to now dimensionalize this map and create an hypothetical V6 3-liter engine from this 2-liter engine? And so that's the end of the exercise. Okay. Now I'm going to say a few words about, since I spent so much time talking about the GM2 mode, I think it's appropriate for me to talk a little bit about the Voltec system. And there are 2 generations of the Chevy Volt. And by the way, there is also a bit of a misconception. When the marketing people at General Motors first announced the Volt, they talked about it as an extended range electric vehicle. They were basically saying the Volt is an electric vehicle that is a plug-in hybrid. It has a generator that can provide extended range when you need it, but it's real. That was never true. That is not an efficient way of doing things. An extended range electric vehicle doesn't make that much sense for a passenger car. That's a series hybrid. And it's truly not a very efficient way of doing things. What really happened in the first generation and then second generation Voltec is that these were evolutions of the GM2 mode hybrid. What was different relative to GM2 mode hybrid was some of the architectural and mechanical arrangements and the fact that the Volt was designed as a plug-in hybrid electric vehicle, so it was designed to have a larger battery pack and the ability to drive in pure electric mode. So let's take a look at what the Chevy Volt looks like. So here is a small gasoline engine. Notice immediately clutch, clutch, clutch. Okay, so first of all, there are immediately 3 clutches here. Then there are 2 electric machines, MGA at 55 kilowatts, MGB at 111 kilowatts. And notice that MGA is connected to the ring gear, whereas MGB is connected to the sun gear. Finally, the mechanical output of the engine to the wheels comes from the carrier. So the first generation Voltec was essentially a configuration shifting EVT with a single planetary gear set. And it was designed so as to provide the ability to give you excellent electrical performance. In other words, you need to have enough output power so that when the vehicle is operated as an electric vehicle, it feels good. And how many of you have driven a Chevrolet Volt? No one in this room. That's too bad. Former colleague who has since retired, Don Butler, who used to work at Carr, had one. And he was quite happy with it. And it's really quite an impressive piece of engineering. It's something that is worth looking at and driving if you have a chance. Now, the second generation Voltec, and here I have some good pictures as well, is now always equipped with an internal combustion engine, slightly higher power. Also has two motors, MGA and MGB. I'm going to use two different colors for these two. It also has clutches. Turns out that it has two clutches. And now, however, it is not only a configuration shifting EVT because of the clutches, it is also compound EVT because it has two planetary gear set. So let's follow the path. What happens now is that the engine is connected to the ring gear of the first planetary gear set. MGA is connected to the sun of the second planetary gear set. The carrier the carrier of the first planetary gear set is connected to the carrier of the second planetary gear set, and MGB, the second electric machine, is connected to the sun of the second planetary gear set. Further, by using the clutches, I'm sorry, I said two clutches, but there is actually a one-way clutch here as well. Okay, and that's important because in theory, if you didn't have that, you could cause the engine to spin backwards. And anyone who knows anything about engines understands that that's not a good idea. But from a configuration shifting perspective, clutch 1 and clutch 2 are the important ones. I also want to point out that in this configuration, when the vehicle drives in electric mode, MGB is the one that is going to give you most of the oomph, both in accelerating the vehicle and in providing braking regeneration. So what General Motors did was, first of all, it's a larger machine, 87 kilowatts, and it's a rare earth motor with magnets made of neodymium iron boron. Neodymium is a rare earth, so is boron, I think, and the point is that these are expensive magnets. Now, their coercivity, that is their ability to give you concentrated magnetic flux, is excellent, so they're really powerful magnets, but they're expensive. So it is useful to have these, especially for driving in the city, low load, low speed. On the other hand, MGA is made of more economical ferrite. Ferrites are ceramics, they're inexpensive, but they don't have the ability to concentrate flux the way rare earth magnets do. So the idea now is that by a combination of these two different gear sets and clutches, you can achieve a number of different modes. The system is quite well integrated. You can see here, this is just part of the picture, but you can see here MGA, which is blue, it's right here. MGB, which is green, is right there. Of course, how they're connected to shafts, you can see here that there are also silent chains. The configuration mechanically is pretty complicated. And notice that you've got power electronics that are integrated into the same package. That's where the technology is going today. In the old days, you used to have an electric machine connected somewhere to a shaft, and then in some other place you had an electric drive, an inverter or something that then through high voltage cables would be connected to the electric machine. If you can do everything internally, you're reducing cabling, you're reducing losses, you're reducing cost and complexity. It's a good idea. What is it that you're making more difficult? How about thermal management? Whenever you package things more closely to one another, you have more heat in a smaller space, right? So you're going to, so advantages of this tight integration is that you are removing the need for any lengths of high voltage cables. Copper is expensive too, but you are going to present some challenges with heating, or cooling, I should say. No challenges with heating, that's easy to do. So here is one mode of operation for this system. You could, in this configuration, have both or only one of the two electric machines provide power to the wheels. The easy way is if you close this clutch and keep this one open, the top part of the diagram is irrelevant because the clutch is open, but now with this clutch closed, you're going to basically be able to provide output power to the wheels. CD1, this mode of operation right here, is a one motor EV. Low to medium torque works well. This is a high efficiency mode. When you drive in the city and in suburban settings, that's what all you're going to need. Mode CD2, it is also possible, actually, with the same configuration, to also provide, if I now start providing torque with these machines, remember that the two carriers here are connected, and so here I have locked the ring is locked, and here I can transmit torque through both. So in the two motor EV, at any speed, if I have higher torque demand, the hard acceleration, and I want to provide performance, I can now add torque from that electric motor. In all this, the internal combustion engine is doing nothing. Now you have a low extended range mode. This is an input split configuration, okay? And now what happens is that you're going to have to bring in the internal combustion engine. Why? As long as your battery pack has sufficient state of charge, you don't need the internal combustion engine. This vehicle is designed to be an electric car and to give you enough performance. However, what's going to happen now is that in this low extended range mode, if you have reached, let's say, 25% state of charge in the battery pack, well, now you're going to go into some kind of a charge sustaining mode because you don't want to lower the state of charge of your battery pack anymore. You want to keep it. I'm using 25% as an example. It could be 20%, some other number. But the idea is that now that you've reached this acceptable lower limit, you're going to want to maintain that state of charge. Yeah, you could go plus or minus 5%, something like that, but you don't want to do more than that. So in this case now, you need to bring in the engine, and you have a hybrid mode. And this is going to be an operation that, you know, when you're in a charge sustaining mode, so to speak, gives you the low end. You can then have a fixed ratio extended range. Now you have the ability to send the full output power to the wheels. And what happens here, and this is what the Toyota hybrid system cannot do, whereas this system that is a derivative of the GM two-mode hybrid can. If I am now in charge sustaining mode, I have used up my electric range, 40 miles, 50 miles, whatever it is that you can get from the Volt, and I am driving on the freeway, the most efficient way of transmitting power to the wheels is to simply use the engine. There is no reason to circulate electrical power, and so you can have this fixed ratio. There are no electrical energy conversion losses. Then you can have high extended range or compound split, and this is a situation in which you might have high torque demand above 110 or low torque demand above 60 kilometers an hour, and so this gives you a higher gear ratio. So this is something that might be, again, effective at relatively high speeds. So what I have done today has been to introduce the idea of electrically variable transmissions. Electrically variable transmissions use planetary gear sets, one or more. They may use clutches, and they use two electric machines. And as a general principle in the hybrid operation of the electrically variable transmission, one electric machine is used to vary the reference speed about which the other speed ratios take place. This is, in a sense, a way of causing the engine to stay, forcing the engine to stay in a high efficiency, low fuel consumption region. So the regulator electric machine is the one that performs the CVT, continuously variable transmission ratio. In addition to that, the second electric machine is capable of providing torque, assisting the engine, launching the vehicle in electric mode, and doing all kinds of other useful functions. The beauty of the system is that thanks to the flexibility of having this regulator machine provide a much wider range of speeds for your planetary gear set, you're able to achieve a speed ratio, maximum to minimum speed reduction of this transmission that is as much as 10 to 1. So if you were to look, I talked last time about mechanical or hydrostatic continuously variable transmissions. Realistically, a mechanical or hydrostatic CVT can give you a 5 or 6 to 1 ratio. So probably the single most important benefit that you get from a hybrid system like this is in the fact that you have a continuously variable transmission that has a significantly wider ratio of speed ratios so that you can preserve the operation of your engine always in a very desirable operating point from a fuel economy perspective. That is probably the single most important thing. Add to this that you can do regenerative braking, electric launch. If you've ever driven a Toyota Prius, when you're driving in the city and you're creeping, right, you're in traffic, and you let the vehicle take your foot off the brake pedal, that'll happen electrically, that creep, that slow creep that you do when you're in dense traffic. Yuvraj, you have a question?
Professor, while in the Toyota hybrid system, when we are trying to regenerate during posting or during braking, if we are trying to regenerate, and from MG2, that's understandable that it can regenerate easily. But if we want to say regenerate through MGA, which is connected to the engine, and the engine braking has a role to play because the engine is always connected to the driveline. So, are there any huge losses during engine braking which should have been regenerated?
Right. So that's a very sophisticated question, Yuvraj. What happens is that when you have engine braking, you should be able to recover some of that deceleration. First of all, compared to the kinetic energy that you can recover from vehicle motion, engine braking is small. So first of all, that is not such a big deal. But you are right in that that is a potential limitation, because while in principle you can do energy recovery with both electric machines in the Toyota system, in practice you need the regulator motor to regulate speed, and so you're not going to be able necessarily to use it for regeneration as much. But I think that's an increment, that's an epsilon, it's not a significant component. Now, Yuvraj knows a little bit more because he and I worked on some things this summer, so he's more familiar with the Toyota hybrid system than you are, but don't give up on it. This was today's introduction to EVTs. There will be at least one full lecture dedicated to an in-depth analysis of the Toyota hybrid system. So for today, I say happy Friday and happy weekend to all of you, and no lecture on Monday. I'm at a conference. Wednesday, I will see you again in class.